Hi, this is a tip and trick sort of video for the 4A worksheet number 5. Yes, this is the giant mastiff hung from 2 cables from the ceiling. What a stupid question. Well, what we know is that the cables are not at the same angle, but they are at 90-degree angles from one another. What we also know is that the force of tension in one cable is equal to twice the force of tension in the other. So I'm just going to note a few things up here as sort of our what we knows. Theta 1 does not equal theta 2, and F of T1 equals 2 times F of T2. Now, to be honest, I can never keep straight which is the larger force of tension until I solve it. I think in looking at it that actually this is the larger force of tension, but it doesn't matter because we'll come up with a number and then we'll be able to figure out which is which. So I'm just going to go ahead and leave my designations as they are. It's also useful to note that we have, of course, force of tension on the x and on the y-axis, and that the force of tension on the x-axis, if we remember that we can move vectors perpendicular or parallel to themselves, the force of tension on the x-axis is going to be equal to the force of tension times the cosine of theta, assuming that we're using a theta, which is the angle that the cable makes with the ceiling. So because those thetas are not equal and the force of tensions are not equal, we're going to have F of Tx1 equal to F of T1 times cosine of theta 1, and F of X2 equal to F of T2 cosine theta 2. Okay, that's some basic stuff. Now, you probably know, you should know, that if this thing is not moving side to side or up and down, it's in equilibrium on each axis. Well, that's good, that's helpful. And the only axis on which we can actually sort of get a grip on something other than the force of tension, which is what we're asked for, is the x-axis, because of course we've got the force of gravity, which will get our mass involved, and that gives us something to hang on to. But before we can do that, so you should go ahead and do a sum of forces on the y-axis equal to 0, which is equal to Fg, which is your force down, plus plus F of Ty1, which is going to be up, plus, F of Ty2. And you'll figure out the trig functions for all of those. That's how you're actually going to solve for your force of tension, but in order to do that, you still have to have those angles, those thetas. So I'm going to set that aside for a moment. The secret to solving for theta actually lies in the sum of forces on the x-axis, and we know that it's 0. And we also know that it's equal to the force of tension x1, which is going in one direction, and the force of tension x2, which is going in the other direction. Okay, that's fine. So we know we can now we can just ignore that for now. So we know that force of tension 1 times the cosine of theta 1 plus force of tension 2 times the cosine of theta 2 equals 0. Well, this is not revolutionary, but we have this piece of information up here, which will allow us to get rid of one of those variables. So I've substituted in force of tension 2 for Ft1. So now I have an equation that only has force of tension 2 in it. That's helpful. Okay, this gets me to a point where I can factor out force of tension 2. And now, this is a bit of, well, it always seems like a bit of trickery, but it's just algebraic fancy footwork. If I divide both sides by F of T2, there's a puff of smoke and a flash of light, and F of T2 just disappears because anything divided by 0 is still 0. Cool. So we've got 2 times the cosine of theta 1 plus the cosine of theta 2 equals 0. Now I'm going to ask you to join me in a little bit of, we'll call it sort of geometric wool gathering. Yeah, let's do a sideline. So So I've drawn a little right triangle here with theta 1 and theta 2, which are not equal, and sides labeled A, B, and C. Would you agree with me that theta 1 plus theta 2 must equal 90? Of course you would. Okay, well then, would you agree with me that theta 1 equals 90 degrees minus theta 2? Okay, good. That might be useful. We'll just consider that and set it aside. This is some very basic trig. Would you agree with me that the sine of theta 1 is equal to A over C and the cosine of theta 1 is equal to B over C? I thought you would. Now, could I get you to agree that the cosine of theta 2 is equal to A over C? Huh. Same as the sine of theta 1. Could I get you to agree that the sine of theta 2 is equal to B over C? Huh. Same as the cosine of theta 1. Well, that was an interesting little diversion. Let's set it aside. Okay, back to the task at hand. So we have 2 cosine theta 1 plus cosine theta 2. Oh, well, wait a minute. We could do a substitution here. Okay, so 2 times the cosine of theta 1 equals the cosine of 90 minus theta 1. Theta 1 is equal to 90 minus theta 2. Theta 2 is equal to 90 minus theta 1. Hey, wait a minute. Wait a minute. Well, that means that this, the cosine of the other angle, would be equal to the sine of theta 1. Huh, well, isn't that peculiar? So we could substitute that in. I'm sorry, that does look like division. It should not. So let's just do a substitution. 2 times the cosine of theta 1 plus the sine of theta 2 equals 0. Okay, wait, I think we can go someplace with this. Sine of theta 1 equals 0 minus 2 times the cosine of theta 1. So we can, of course, get rid of this 0 altogether. Okay. Well, is there a way? Now we have just a number and 2 trig functions. If only there was a way to divide both sides by cosine of theta 1. Aha! Now we have, what is this? Well, it's actually, of course, the tangent of theta 1 equals negative 2. You can solve this using the inverse tangent function, and you will have a numerical value for one of your angles. You can then use something like this to find the numerical value of your other angle. Hey, that wasn't so terrible. Have fun.